Hello everyone. Today's video is about the definition of the span of a set of vectors. It's an important concept that will stay with us for the rest of the class. Here comes the definition, and then we'll look at some examples. If I give you a set of vectors, denoted S, a set of non-empty set of vectors, U1 through UK, then we say that the span of S is the set of all linear combinations of vectors U1 through UK. It's written very briefly here with mathematical notation. The span of S is the set of all those vectors in Rn that are combinations of U1 through UK. Let's have a look at some examples. I can take this set here of vectors, 1, 1, 1, 1, 2, 0, and 1, 2, 1. Saying that a vector belongs to that span means that there exist constants A, B, and C such that I can write the vector as a linear combination in the following way. C, 1, 2, 1 for some A, B, and C in the real numbers. Here are a few examples. I could make some choices. If I pick A and B to be 1 and C to be 0, then the linear combination I get is 1, 1, 1 plus 1, 2, 0 plus 0. In other words, when I add these together, I show that 2, 3, 1 is a vector that lies in the span of S. Other possible choices for these coefficients, 0, 1, minus 1. They give the vector 0, 0, 1, which also lies in the span of S. All possible choices of A, B, and C give all the possible vectors that lie in the span of my set S. We can think of spans as some geometric objects, so we can graph them. Here's a little example. Let's consider the span of the set containing a single vector 2, 1. It's drawn here. All the vectors that are linear combination of 2, 1 are just multiples by a scalar of the vector 2, 1. Writing down all of the multiples of a scalar is equivalent to considering the line parallel to the vector 2, 1 passing through the origin. Here's an elaboration on this example. What if we were to consider the span of the set S2 that contains 2, 1 and minus 4, minus 2 as its vector? It's drawn here graphically. There's 2, 1 and there's minus 4, minus 2. You see that they're parallel vectors. They have the same direction. And in fact, the span will still contain only the vectors that are on this line. The reason why that's true is that, as I just said, these vectors are parallel. In particular, I can get from one to the other by multiplying by minus 2, for example. Well, minus 1/2. Therefore, whenever I write a linear combination of the two vectors, I can write it as follows. This is the same as saying that this is A times minus 1/2 times minus 2 minus 4. Oops, I wanted to write something different. Let me write it like this. Minus 4 minus 2 is negative 2, the vector 2, 1. So I can plug that into the expression here. 2, 1 plus B times minus 2 times 2, 1. By substituting minus 4 minus 2 in minus 4 minus 2, this expression here. In other words, all I get here is by factoring out A minus 2B times 2, 1. And that is an element of the span of the set S1 that only contains the vector 2, 1. In other words, the two spans of these two sets of vectors are the same, despite one containing one vector and the other containing 2. Let's have a look at another example. Here now, the set of vectors is the following one, the vectors 2, 1, and the vector 1, 0, which are plotted here. My claim is that the span of this set of vectors, these two vectors here, is the whole of R2. How can I convince you of that? Well, I will give you a graphic justification. If I take any element in R2, it's just any point in the plane, I call it V, and I'll suppose that it has components V1 and V2. Well, then I can write V as a linear combination of the vectors 2, 1, and 0, and 1, 0 as follows. I'll draw a parallelogram like that, and then I can consider the following vectors. This vector here is nothing but a rescaling of the vector 2, 1, which is the vector in blue. That's 2, 1. And I don't know by how much I'm rescaling that vector, but I am. And I can write the light blue one as some constant times 2, 1. Similarly, I'll use orange. I can rescale this vector 0, 1, which is the red vector here, to get some multiple of it, which is b times 0, 1. And you see, I chose them to complete the parallelogram that we have here, whose top vertex is v. In other words, what I've written there is that v is equal to a times 2, 1 plus b times 0, 1 for some a and b real numbers. This is a justification. If you're not happy with it, we can also think algebraically. And algebraically means to set up a system as follows. I would like to write V1, V2 as a linear combination and allow me to use x's and y's here. V1 and V2 are constants, x's and y's are variable. If this equation here has a solution, then that means that I can write V1, V2 as a linear combination of the other vectors. If I expand this out, I get 2x plus 0, V2 is equal to x plus y. Now, this is a linear system of equations, and these are two lines, L1 and L2. It's not difficult to check that the two lines have different slopes. And if two lines have different slopes, then they must intersect. But if they intersect, this linear system has a unique solution. In other words, V can be written as a linear combination of 2, 1, 1, 0. It doesn't matter what V is, any arbitrary V in R2. Now, a remark is in order, especially looking at the reasoning that we did here algebraically. You see that there's a tight relation between spans of vectors and linear systems. Let's make that clearer. If I give you a matrix A1 to AN, these are its columns, then saying that a certain vector B belongs to the span of the columns of the matrix is equivalent to saying that the corresponding linear system AX equals B is consistent. Why? We can just spell all of this out. Saying that B is in the span of A1 AN means that for some coefficients x1 through xn in R, I can write B as a linear combination x1 A1 plus x2 A2 plus all the way up to xn an. Well, but remember that writing this expression, x1 a1 plus dot 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 xn an is the same as writing a times the vector x1 xn. So saying that x1 and xn exist that realize B as a linear combination is equivalent indeed to saying that AX equals B has a solution. And having a solution means that the system is consistent. Let's move on to some more examples. Remember that we defined standard vectors, E1 through En, as the vectors whose entries are all zeros except there's a 1 exactly at the position denoted by the index of the vector. The span of the standard vector is always the whole space. The reason why that's true is that for any vector in Rn, I can write that vector as explicitly writing out its components, v1 through vn, but then I can just write the vector v1 through vn as a linear combination of the standard vectors, each one rescaled by the corresponding component of the vector. Another way of saying this is that if I have a linear system whose associated matrix is the identity, in other words, whose columns are the standard vectors. In this example here, I'm drawing a 3x3 matrix. Then the span of the standard vectors Rn is equivalent to saying that Ax equals V is always consistent for all choices of V. Let's have a look at a couple more examples. Here's a question. I give you a set with 3 vectors in it, and then I give you another vector v. How do we check that the vector v is or isn't in the span of the vectors given in here? Well, we just said that belonging to the span is equivalent to a certain linear system being consistent. So this question is the same as the following. If I set up a matrix A whose columns are the columns coming from the given 3 vectors, 1, 1, 2, 3, 4, and then let me augment it already with the vector v. So I'll call this A and this is v. The question is the same as asking whether the linear system Ax equals V is consistent. To answer that, we need to look at the reduced row echelon form of this matrix here. And that's why I wrote down the augmented matrix. Let's compute that. We have that. This looks like a column of 1s, but it's really just the separation. To reduce row reduced, I will have the second row minus twice the first in here. So I get 0, and then I'll have minus 3, 0, 1, minus 4, that's negative 3. Then for this third row, I will just subtract the first. So I get 0, 1, 2, 1. For the fourth row, I will subtract the first row to get a 0, 0, 3, minus 3. Okay. Now, we can clean this up a little bit by rescaling the first and third row by, well, I will divide the second row by -3. So I get 1, 1, 1, 2, 0, 1, 0, 1, 0, 1, 2, 1. And the third row will be 0, 0, 1, -1. I like this because it is cleaner. We settled the first column. Now let's take care of the second pivot column. I'll use the 1 in the second row, this pivot position right here, to eliminate the rest. To do that, I'll obtain the following matrix. We have 0, 1, 0, 1. Up here, I will replace this with R1 minus R2 to get 1, 0, 1, 1. Then I will subtract R2 from the third row as well to get 0, 0, 2, 0. And I'll have my fourth row, 0, 0, 1, -1. We're almost there. Now, allow me to take this third row and rescaling it. So I divide everything by 2, which effectively just makes that 2 into a 1. For posterity, I'll write this. I'll write a 1/2 there so that we remember. Now let's use the third row to eliminate the 1 in the fourth. 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 0. And in the fourth one, by subtracting the third, we get 0, 0, 0, -1. What we know about the row-reduced echelon form is that this row over here is problematic because we have zeros in the variables and then a non-zero entry in the constant. This means that the system is inconsistent. The system AX equal V, which is equivalent to saying that V does not belong to the span of S. Let's have a look at another example. We won't compute anything here, but it's going to be a conceptual work. In a similar spirit as what we just did in the previous example, if I give you a set with 3 vectors in it, then if you wanted to check that its span is equal to the whole R3, that's the same as saying that every vector in R3 is a linear combination of those 3 vectors in S, which is the same as saying that AX equals B is always consistent when A is the matrix whose columns are the vector of S. For that to be the case, we need the reduced row echelon form of A to be an identity matrix. Now, at this point, you see that it's very important for this sort of questions to understand the reduced row echelon form, but you probably also learned that it's a very lengthy computation and a little bit annoying to do. So what we're going to develop next are faster methods, in particular easier than computing the row-reduced echelon form, to understand the span of a set of vectors and to understand when systems are consistent or not. We would like to do that efficiently without having to compute the row-reduced echelon form every time. I'll explain that in the next video.